All right, I don't really have any business. We're going to talk about orbits and gravitation and gravity, and we're going to kind of build up uh, the picture that we're left with today, which is also quite uh, painfully incomplete, but we're going to try to see how we got where we're at, and we're going to go all the way back to the Renaissance to do that. But before we do that, why don't you guys say hi, first of all. Let me see who's here and remind me where we're at in our story, what we did last time. Questions, concerns, things that were interesting from last time, loose ends, things that you walked away thinking about, anything. Um, and remind me your name again, too, so that I'm still not there yet. I got a few of you, but I don't have all of you. Not in this other room, yeah.
They didn't like it was a lot on my telescopes and websites and icons.
Yeah, I'm not totally sure how long it was. It wasn't a tremendous amount of time. They had lenses for glasses. It's almost more surprising that it took them a long time to realize that if you took two lenses and put them in front of each other, you could actually see great distances. I think they were using them for navigation a little bit, like the pirate's scope kind of thing. Um, but I'm not sure how long it was. We could probably look that up. Yeah, yeah, Isaac.
They're just like you showed, like the haplogroup X.
Mm.
It might, it's not a fake grouping or anything like that, but that's just a crazy idea to be just thinking about, like that was somehow they somehow made it all the way there. Like
It's
just
pretty
thinking
weird.
that's like
Yeah.
so wild.
Yeah, I've been thinking about that one a lot too. Yeah, that's very, very bizarre. I mean, look, like the past is almost more difficult to understand than anything. It's one of those weird things where you can't just run like a test tube experiments on a lot of these. You're always trying to look at the evidence and make arguments based on what you find. Yeah, Dante.
Apparently it was less than a year.
What was less than a year?
When
Oh,
between
between the telescope?
telescope
Really?
when Galileo
Wow. Okay, so he was kind of on the edge there.
invented and later patented.
Okay.
And 1609 is when Galileo pointed at this.
That's wacky. But they had lenses for quite a while before that, huh? Hundreds of years. Okay, that's where the real wildness is then. So nobody thought of stacking them. That's totally bananas. Yeah, Max.
Thing I remember about last week, and I believe we talked about this last week, but I know there was a video about it in the big YouTube watch list where we're talking about like how they were discovering that the Earth is not flat,
Mm.
doing two stakes in two different locations. I just thought that was really cool. I think
Yeah, we talked about that at the beginning of class last time.
I just never thought about like it put two sticks in two different places and one would have a harsh and then it based measured off the sun. I just thought that was
It's really, really simple and clever, yeah.
yeah,
That's really, I think, the beginning of mathematical physics,
it's
really.
like so simple.
So simple.
So efficient.
It's really wild. My wife and I are working on a book right now, and we've had to go back and read a lot of the very early physics papers from the 18th, 19th century, and it's crazy how easy they are to understand. There's something very strange that happened in the 20th century where physics became kind of impossibly impenetrable to like people who hadn't studied, esoteric mathematics for decades. It's very, very interesting how some of the early history of thought is just so simple, very clear. Yeah. Well, hold on one sec, Dante. Corey, right? Yeah. Okay.
I think to some degree that could be that we ran out of simple problems at some point, and most of the solutions we have to any of the mysteries left, we maybe aren't searching for the simplest solution so much as just a purely proof that it works through math.
Yeah, I mean, I think there is some of that, but I also think that I think that we have the Ptolemaic versus Copernican problem. I was actually hanging out with this very famous quantum physicist this morning. She works at Oxford in London, and she kept saying like the work that we're doing is mathematically rigorous. It's conforms to the evidence. And, I actually waited until the back half of the interview to bring this up, but I was like, yeah, but so was the Ptolemaic system for 1,000 years. It was mathematically rigorous. It conformed to the data really tightly. By some accounts, it was more beautiful than the alternative. So you still have that weird blind spot where you can be totally rigorous, totally ingenious about how you fashion your quantitative solution to the problem, and you can be totally wrong at the same time. That's a wild blank spot. And I've been really trying to understand too, and we'll get into this a little bit more in a second, like what it was about guys like Copernicus or Kepler, who we're going to talk about today. What was it that made them even want to buck the status quo? Like, why were they unhappy the uh, with the Ptolemaic system? And it's hard to understand because they're all deeply religious people, right? And it seems like they almost thought that the Ptolemaic system was too complicated, like God wouldn't like it. It wasn't simple enough, something like that. It wasn't elegant, you know. Tansia, yeah.
The first wearable lens was invented in 1284. So
Wow, so a few hundred years, really, right? That's wild. That's really crazy. I mean, they had glass. It's crazy that lenses took that long to appear because, you know, like the Phoenicians were known for their fantastic glass work. People had glass windows back in the first millennium BC, but that they wouldn't have used them as lenses is wild too for 1,000 years. People are weird. Right. Okay. So we'll get into these people's heads a little bit more in a second. What else? Any other outstanding? Yeah. Remind me your name again. Abigail. All right.
Right, so we talked about quite a bit on Tuesday, but I thought it was just interesting is the amount of stories with the constellations and then how many different stories there are for the same set of stars.
Yeah. Yeah, sometimes they're the same, sometimes they're different, but oftentimes each culture kind of has a different one. The one example that stood out to me was the bear thing, which I thought was really weird. Um, which again, I have no coherent idea of what played out exactly, but it's pretty bizarre. What else? Yeah, remind me your name. Nolan.
Um, last was we were talking about the geocentric versus like geocentric views on how we look at and just how they made that whole loop for the pressure gradient markers
Mm-hmm.
deeper than the center. It's like I remember you saying about like I've never seen like the product curve. It's like
Yeah.
the geocentric is actually circles. Just seems to be
Well, the first version was actual circles. That didn't work out, so they had to squish the circles a little bit. Our orbits, we now understand them as being sort of elliptical, but they are almost perfect circles. Like we call them ellipses. I'll show you some pictures of them later. I mean, they're very, very circular. The difference between how close we are at one end versus the other, like Earth to the sun, is not really even appreciable compared to our tilt. So yeah, what do you think, Nante? You look like you were sitting on a thought. All right. It is weird though. But you can see how it's beautiful too. I wish I had a good example of the trochoidal patterns. I mean, the patterns that the planets would be etching out in the Ptolemaic system were these beautiful floral patterns, right? Like you can see how people would be attracted to it. And you know, there's still this attraction in fundamental physical theory towards beautiful mathematics and elegance and these weird terms that seduce people's attention. But I don't know. I mean, I guess I'm still struggling with this myself, like how you can tell the difference between, you know, like what incites you to think there's a problem in the first place. That's really odd, you know. I could see people have just gone along with the Ptolemaic thing right up until Galileo points his telescope at well the phases of Venus and sees that something doesn't make sense. But that's not what happened. People naturally pushed back against it, right? So we kind of ended last time with the phases of Venus. I actually had to get up so early this morning that I actually saw Venus. And Venus is actually in this gibbous phase right now. So I remember telling you guys, I was like, oh yeah, if you get a scope, you can actually see the crescent of Venus. So I grabbed my scope this morning and I looked at it. And I was like, oh no, I actually can't see it. And I felt really bad for telling you guys that. But then I realized that it was actually leading the sun, and so it was in this gibbous phase, and that's why you can't see the crescent. So actually, Venus, if you want to see the crescent, um, when it's actually closer to us, it's much bigger because when it's full, it's on the far side of the sun. And so you can actually get a really good view of Venus when it's in crescent phase. Yeah.
I think what might have led people like Copernicus to have a problem with the Ptolemaic system was that it changed so much. They kept having to change
Yeah.
and change
Yeah.
because it what didn't work. It kept on failing.
Mm.
To
Mm-hmm.
the
Mm-hmm.
point where it like if it really was perfect, if the role was really perfect, why would it be keep getting wrong?
That's a good point. I think that's really I think that's really astute. That's really onto it. Yeah, I think they kept having to adjust it. Stuff like that happening today too. I think we'll see more of that in the cosmology section. That's where I see the most adjustments happening, kind of on the fly. Um, is there some of that going on in fundamental physics? Not so much adjustments. Yeah.
So you mentioned that you said you got it this morning, solving this, right? What do you do that often where you can just like you just get up or you like when you go out at night you just kind of see the planets? Like is that like a common thing?
Yeah, I mean Venus is a really interesting one. So
I was gonna ask like what would you say is like the hardest one to really spot?
well, the bummer is that some of these orbits take forever, right? So they're hundreds of years for some of the far out planets. So so like 1 year, like right now we don't have a very good view of Jupiter or Saturn, but in years past those have been just beautiful. Like you could take your scope out and see the moon. The moon's going around Jupiter. It's really amazing. But I think it's going to come back around later this month and might start to become visible. But basically, it's out during the day, so you can't see some of these planets.
Is it,
Ve- Good, yeah.
is it different depending on like the atmosphere? I'd assume like the southern hemisphere would have a better view of them at that point.
I don't know that that would really affect things because they're in this plane called the ecliptic, right? Which should be visible from both sides, depending on which other side of the disk that you're on. You would just see it from the bottom versus the top of the ecliptic, basically. Um, Venus and Mercury are kind of cool though. They're kind of always there, but they always appear in the morning or at night. Because if you think about it, like when the sun's rising in the morning, you're actually seeing, like right now, I can see Venus in the morning because it's on that side of the sun. So it kind of rises before the sun because it's actually on that right side of the sun, basically. So I see the sun start to rise, but Venus is actually going to rise in front of it. And then at some point, the sun gets so bright, it just kills off any light from Venus. You can't see it anymore, but it's still there. Venus is just in front of the sun. And then what will happen is Venus is going to go behind the sun at some point, and then I'll start to see it at sunset when the sun starts to dip down. Now I see Venus on that other side, basically. And it's this whole cycle, I think it's like 200 something days on one side, 200 something days on the other, and it disappears in the back for a little while. And the same thing, Mercury is the same way, but since it's even closer to the sun, it's harder to see. It's basically only in the sky for just a few minutes, usually in the morning or at night. And you can't really, it's a very, very hard one to catch. You have to get lucky, basically.
That makes sense that those would be the most consistently easy to see because they're closer to the sun.
They're closer to the sun, yeah, and their orbits are fast, and yeah, these guys that are far out, you kind of have to get lucky. So you have to wait for either the Earth to move into the right place. You're not going to wait for them to move into the right place. So you got to wait for the Earth to catch up, basically, to wherever they're at. And so it's kind of there's kind of an annual cycle for when you can catch those guys. And then it might, yeah, then still you're dealing with the nighttime versus daytime. I don't know, it's tricky. I've been kind of just paying attention to it more since I've been teaching this class last few years. You guys should get those little star finder apps. It's kind of fun because you can, just when you're out, just check it out and see if there's any planets that you can pick out. And once you use them a little bit, then you start to just notice them. Um, but yeah, it's interesting. So some of these are much, much, much more visible when they're on this close approach to us, right? So Venus is one of those. Mars also can be really, really big and full, depending on whether we're kind of overtaking it in its orbit. It can also be really tiny and hard to see. So yeah, that's kind of fun. Yeah, I don't know. I recommend you pay attention to this. But yeah, I just thought of that because Venus saw it this morning, and I was like, ah, that's interesting. This is what kind of sealed the deal with the debate that we were talking about last time. All right, let's what else? Anybody have any other thoughts? Any loose ends from last time? We can kind of keep the story moving otherwise. Anybody? All right. All right, stop me if you have thoughts along the way. So I want to kind of move. So let's assume, um, to some extent, that we talked about Copernicus had this cool idea. He self-published it at the end of his life. The reality is that nobody really bought it. I can't get in his head. I think um, Dante's point that he was probably fed up with all of the ad hoc adjustments to the old theories probably motivated him to write this book. I actually haven't read his original book, and I really want to, so maybe I'll do that, and then I'll get back to you. Anyways, it wasn't a popular idea. Galileo famously threw it in the face of the church. That didn't work out for him. The first time that we see it really taken seriously is in the context of these two gentlemen. So this is kind of the story of Tycho and Kepler. And Kepler is kind of the first person to really make an argument that people actually begin to take seriously. And so let's see if we can make sense of how that happened. So Tycho and Kepler were two very different people. So Kepler came from a really, really, I wouldn't say a really impoverished background, but he wasn't wealthy at all. He kind of realized he was very quantitatively smart from a young age and made a living by traveling around town to town tutoring kids who were in their version of the university system at the time. And Tycho was the complete opposite. He was this wealthy baron who lived in a castle, hosted huge events all of the time. Um, Kepler had all of this interest in this new Copernican system that was kind of fringe science at the time. Tycho, on the other hand, had spent his life compiling this enormous star catalog, reputedly the best star catalog in all of Europe. So he made measurements of the sky as a hobby, I suppose, and he had kept all of these records that couldn't beat anybody in the land. And Kepler knew about this, and so he sort of made a pilgrimage out to see Tycho and thought, hey, if I could examine your records, maybe I could actually test out this Copernican system. This is as well as I understand the story, anyways. I forget who it was. Somebody last time, maybe it was Dante or maybe it was Corey. Somebody over in this region pointed out that basically Kepler had to wait around for Tycho to die before he got access to all of the information. This is kind of true. Tycho was really protective of his data. Tycho also had his own model for the solar system, which is worth pointing out. It wasn't you? Yeah, I thought it was somebody. It was Isaac. Yeah, somebody. I was like, somebody up here pointed this out. Yeah. So it's a little bit more nuanced than that, but so why wouldn't Tycho want to let Kepler check out his data, right? This is weird. We would, think he would. Well, Tycho had a different idea. He thought, okay, well, Galileo's, um, I'm not sure that the observation of with the telescopes had happened yet, but he figured that he could sort of rescue the geocentric system by saying, okay, well, Venus, maybe we'll just go back and look at it. Venus can go around the sun. Mercury can go around the sun, but the sun goes around the Earth. So he had like a two-axis solar system model. He was like kind of trying to walk that tightrope between both systems. So that was Tycho's pet project. He believed that this model was correct. And so maybe he wasn't interested in supporting Kepler originally because he didn't want to see his own picture thrown out. I have no idea. But for whatever reason, yeah.
Tycho's.
Geo, yeah. So in Tycho's system, I guess I could draw it, but it's probably easy enough to explain. He imagined still that the interior planets, like Venus and Mercury, went around the sun. So no problem with this kind of crescent behavior or anything. He was like, that's fine. But the sun and Venus and Mercury, the sun and its orbiting planets go around us. So the Earth is still at the center of the solar system, but it's kind of a biaxial solar system. There's an orbit around the sun, and there's an orbit around us. And we're the central orbit. So the church liked that, but he was also able to, I think, deal with some of the contention about some murmurs about how the Copernican system might solve this kind of an issue, basically, which was Galileo's principal argument initially, was this phases of Venus thing. So, which I imagine, I think was an argument for a long time before Galileo. Galileo just kind of proved it when he pulled out the telescope and showed it. So, anyways, so Kepler shows up. Tycho lets him look at the records off and on. He's kind of supervising him, doesn't let him get too involved. Tycho dies after like a year once Kepler arrives, which is really weird. He also he seems to have died because he had to pee really bad in the middle of a dinner and he just refused to do it and his bladder exploded, which is absolutely terrifying to me. Um, Sometimes I feel like when I'm up here for an hour and a half, I have to pee. So I might actually do that if I have to from now on, because I didn't realize you could die from holding your pee. But apparently yeah, I don't know. It's apocryphal. I don't know if that's what killed him. Maybe he was poisoned. He was a weird dude. He also he got in a duel over like a math equation when he was in college. So dueling used to be how you settled disputes back then, apparently in college. Um, Now you're probably it's probably just like Mean Girls on Facebook or something. I don't know where.
People being like, let's take this outside and we'll fight you.
Yeah, I guess so. But everybody had rapiers or whatever, and so he lost his nose. And so for the rest of his life, he had this gold brass nose that he wore around, which I always thought would make a great Halloween costume. If anybody wants to try out Tycho this year. So weird dude. He dies pretty quickly after Kepler meets him, and Kepler must have ingratiated himself enough to his host to inherit these star catalogs. And so, yeah, Kepler, trying to get into the mind of Kepler. So Kepler, for whatever reason, seems from a very early point interested in the Copernican system. From what I can find in his own writings, it seems like he also is a very religious person. All these people are kind of arguing from the mind of God, which is a really interesting place to approach. This is generally considered pre-Enlightenment physics too. This is kind of like the Renaissance period. It's not really a scientific method yet. People are just starting to play with these things. Again, nothing like we talked about this Greek project that happened, two and a half thousand years ago. Like this wasn't happening in the West for 1,000 plus, almost, a really, really long time. So this is kind of the reawakening moment, this Renaissance moment.
It's like the rebirth.
Yeah, it is kind of a rekindling. Now there was cool stuff. The people in the library systems in Islam in northern Africa, and they were developing a lot of cool mathematics and thought, but it wasn't really cross-pollinating with the Western traditions in Europe at the time. So while Europe was in a dark age, Islam was in this kind of blossoming phase. Anyways, these guys are kind of rediscovering rationality for the first time in 2,000 years, which is kind of crazy. So Kepler, it seems like, is motivated because he sees the sun as a better representation of God. It's got light, right? Like it's the bringer of life and light and all of this. And so he just is motivated by wanting to put the sun at the center of the universe because that fits better with his conception, I guess, of the way that God would do things. Now, like I said, Kepler got his start as a tutor. So he had a basic appraisal of geometry, right? And of course, these people were starting to really dig up the old ideas of the Greeks, who were some of the first geometers. We obviously talked about a story on Tuesday, which was really simple geometry that allowed these guys to measure the Earth, quite like just kind of incredible leaps of reasoning. And so, as Kepler tried to he tried to check Copernicus's idea against these incredibly accurate star catalogs that Tycho had left him. And it wasn't working out. And at some point, through some flash of revelation, he had the idea that, well, instead of trying to fit circles to these things, what if I try a different conical section? What if I try an ellipse on it? And the ellipses actually worked perfectly almost immediately, and he was able to fit these orbits by essentially elongating the circle that he tried to fit things to. So, you know, that's an interesting flash of insight that doesn't seem to have appeared anywhere prior to this moment with Kepler. And Kepler had no idea still what in the world these planets were doing going around going around the sun. But he seems to have envisioned that the sun had some sort of magnetic attraction to it. Like there was something special about the sun that none of the other planets had. Fair enough. It is kind of a unique looking thing in the sky. Can't even look at it actually. It's so intense. Yeah.
I think you like might have mentioned that one of the last grade was like a little bit off topic. Didn't the Egyptians like isn't it like didn't they build the pyramids like related to the circumference and like it was mentioned that they were like surveyors and astronomers and they used like shadow lengths to align structures and understand like the slows and the cycles.
I think there's a lot of evidence that these, I don't know that I talked about it, but I think there is a lot of evidence that the pyramids were aligned to different structures. I think there's some evidence that they're aligned to the Orion constellation. I've seen that before. I don't know. Um, but or aligned to different pole stars at the time. I think Thuban was the pole star at the time, if I'm not mistaken. It wasn't the Polaris that we have today. So there might have been some alignments with respect to that. Um, but I don't know. The pyramids are really, really weird stuff. The deeper you study the pyramids, the weirder they get. Um, so yeah, I mean, I think people and the Egyptians loved the sun, first of all. So did everybody, though. Like sun worship goes back. You go deep into early history, ancient times. Everybody associates the sun with some sort of powerful deity, and I mean, yeah, the fact that you can't look at it, it makes a lot of sense, right? It's like, what the heck is that thing? It's clearly important. Feels good on your skin. It can burn you. I mean, it's just insane. So, yeah, no fault to these people. What's that? Plants like it. Yeah. I mean, yeah, the sun is insane. All right. So, I don't know if that answered your question. I'm sorry if it didn't, but oh yeah. Well, don't get me started on the sun, whatever you do, because we have a whole semester dedicated to the sun, and it will take that to make sense of it. All right, so he starts playing with the ellipse. That's cool. I guess so. He has this intuition that the sun has some sort of tractor beam, like it's this magnificent thing. Perhaps it's the heart of God itself, and it makes sense to him that the sun could exert this what he calls it a magnetic presence, right? And I think magnetism was the closest thing people could get to attraction without mediators that are obvious. And so he starts playing with the math. So you guys would have gotten some of this in your textbook. I won't belabor it too much, but I think that there's an interesting story here as we work towards a concept of what gravity really means. And so I'll build this out just a tiny bit. Um, so you guys should remember this from your reading, but the way that we draw ellipses is essentially that you have two focal points with them. And this means that you have actually a longer axis as well. It's not like a circle where there's just a center with a radius. You actually have a longer axis on an ellipse. It's kind of an oval, right? And you have a shorter axis. And so the math that's basically used to describe orbits in this system is based on this, uh, let's say, longer axis, essentially, which is the semi-major axis. Now, what Kepler realized, which is a really interesting insight, was that in order to fit his planets onto the ellipse, he had to do something weird with the timing, which was when the planets came near the sun, they went really fast. And when they went away from the sun, they slowed down considerably. And he sat with this realization for a while and tried to come up with the simplest way to describe this in an equation. So this is what it actually looks like. And this, you can see how this would reinforce his idea that the sun had some sort of magnetic attractive thing to it, right? Because it's kind of pulling the thing in and then it slingshots away. And as it gets too far away, then the sun's kind of yanking it back and it gets all this speed as it comes in towards the sun again and then rolls away. And we would, of course, describe this as gravity today. He had no conception of gravity. So what did he do? Well, he realized that what's really happening is that there's a proportionality, and I'll get back to that in 1 second. There's basically a proportionality between the amount of region of this ellipse that's swept out per unit time. So no matter where the planet is going, it takes the same amount of time for it to carve out an area, a region within that actual ellipse. So there's actually a constant piece here. That little wedge is actually the same amount of area as that big wedge over there. They're just shaped differently, right? The result is that it takes the same amount of time to go through the same amount of area of this ellipse. And the way that he ends up putting this down in mathematics is extremely simple. He's basically saying that the time, the period, this is the p squared, is in proportion to the wedge that's carved out, which turns out to be the semi-major axis cubed. So he comes up with this very simple relationship between this by studying how long it takes these planets to carve out their path on this ellipse. Now, this is my favorite symbol in all of mathematics, and we don't do a ton of mathematics in this course, but I think this is one to actually pay attention to. So this symbol looks like a little fish. It actually just means proportional, right? So what's proportionality? It's not exactly an equal sign, right? Because the thing that he also recognized was that each one of the planets did this a little bit differently. So they all swept out these paths, and the area of the section that was swept out was crossed in the same unit of time. But all the planets did it a little bit differently. Some did it faster or slower. Why was that? He didn't know, actually. So he wrote out his relationship without putting an equal sign because it wasn't equal for every planet. He didn't know why, but he knew that it wasn't equal. So this is pretty cool. And you start to see people in the actual university structures at the time starting to actually consider this argument. It's been put forth in a really simple fashion. He's kind of substantiating this more or less piece of fringe science from Copernicus, but he's doing it in a quantitative way that lines up with the greatest star catalog that they have in Europe at the time from Tycho. And he's put together a pretty reasonable, simple law that, people, again, they love simplicity. They think that God would come up with simple, elegant models as well. So it's kind of interesting that Kepler doesn't know what it is that's different between the different planets. It doesn't occur to him what's different. Enter this guy, Newton. So can anybody guess what it is that's different between the planets? Yeah.
Their mass.
Their mass. Yeah, some are bigger than others, for lack of, let's just keep it simple. Some of them are bigger, some of them are denser than others. Now, that's actually a lot more interesting than it seems on its face, because what it says is something like, the sun isn't governing this whole project alone. The sun isn't just this face of God thing that's pulling on everything all by itself and determines how everything will go. The bodies that are being pulled on also have a say in the matter. That's actually quite revolutionary coming from this very religious background, right? So this concept really comes from Newton, although, to be honest, Galileo and many other people were working on the concept of mass ahead of time. And generally speaking, mass was related to weight, how much something weighed on a scale here on Earth. Weight is a super, super ancient idea. I mean, people were using weights for some of the oldest artifacts in the world, going back to the Indus Valley, back to Mesopotamia, where these intricately standardized weight sets, right? I mean, even the way that we defined a kilogram for most of the time that we used kilograms was essentially based on an actual kilogram somewhere. Like they had a master kilogram. I think it was in Paris or something. Don't quote me on that. It was somewhere, but it was insane. They just had a kilogram, and that's what the reference point was for like years and years. It was totally nuts. Um, Now, of course, you can transfer between water, which is approximately has a density of somewhere on the order of 1, so you can actually get a cubic uh, liter of it to be, approximately like a kilogram. There's ways of reestablishing it, but they had a master kilogram for a long time. Yeah,
Yeah, the master kilogram, the international prototype of the kilogram IBK. There was a platinum iridium
yeah,
cylinder
yeah.
known as Le Grand K.
Le Grand K.
It was used from 1889 to 2019.
There you go. That's incredible. Yeah, they switched over. We'll talk about when we get to light and stuff and electromagnetism. We'll talk about the new kilogram. Um, but it is just remarkable. I remember reading about this like in college, and I remember reading this. I saw this article, and it was talking about how whenever they have to use the kilogram to actually compare something, they like they had like one guy carry the kilogram, and they had like two guys like walking behind him, like just in case he was to trip or something, because they didn't want to lose the master kilogram.
So two different glass.
Yeah, it's so crazy, right? So it's like people had this idea that there was that there was some quantitative standard that could be met and you could compare reference against it. So this idea of weight was like pretty well established. And the idea of mass is very, very closely related to the idea of weight. The problem is that weight requires you to be on the surface of some enormous body, like Earth. So it works really good as a concept here on Earth, although it gets a little messy. I mean, the idea of how much mass something has, like a kilogram, for instance, it has basically the same weight all over the surface of the Earth until you like climb up Mount Everest or something and then, well, it's not going to weigh as much. That's weird, but people weren't really fretting about that for most of history. At any rate, Newton, for whatever reason, again, still trying to pry into the minds of these people, um, Newton seems to be the first person who really started to apply this concept of mass to the actual celestial bodies themselves in terms of explaining why some of them move faster than others. So Newton was, in some sense, he's like the first Enlightenment scientist in some sense. Maybe he kind of birthed this new age where it's like, okay, he's still deeply occult, deeply religious guy, but he basically decides, this is the first time you really see this, where he says, I'm not going to bring any of that into my rationalizations of how things work in the universe. That was completely unknown since the ancient Greeks anyways, that people would do that. So Newton kind of sets up this new project, which is very much in line with what happens for the next, say, 400 years, where people try to come up with natural explanations for phenomena and where they can't, they basically just bow out. So Newton, in some sense, sets up this whole new program where we try to make sense of things mechanistically, but at the same time, and we'll see how this plays out, he actually doesn't assign cause to this mass thing at the end of the day. He just comes up with the relationships that scale it. So one of his first real contributions was this concept of inertia. You guys ever hear of inertia? Pretty weird stuff, actually. I don't know if you ever stopped to think about it, but it's pretty weird that, I guess it makes sense here. Like something's heavy, it's hard to move, right? It has some inertia to it. But what's pretty weird is that even if this thing is in outer space, it's still pretty hard to move, right? It's not even sitting on the face of a planet. It could be far away from a gravitational system, but it still has inertia. Like a 100-pound bowling ball in space still feels like 100 pounds. That's really, really weird, actually, if you think about it. Now, he didn't go to outer space, obviously, to make this realization, but he thought about some other pieces of the puzzle. Famously, he did this experiment with a bucket of water where, I don't know if you've probably done this before, but if you swirl like a bucket of water, you see the water climb up the sides of it, right? And he thought, that's really weird. It's like it's almost like the water wants to just stay uh, like attached to something around it, right? Or how about this one? When you like spin your body, like your arms kind of fly out to the side. And he was thinking, that's really weird too. Like, it's almost like your arms are trying to stay attached to your surroundings a little bit. There was this guy named Ernst Mach who really developed these ideas a couple of centuries later. And he really, really thought that perhaps this inertia business came down to the fact that the whole of the universe, at least everything around you, was in some sense gripping onto you and was holding you back or keeping you in whatever continuous state of motion that you were in with respect to your surroundings. So Newton writes up some laws about inertia, but he has no idea really what causes it. It drives him crazy. Um, what else? Newton also talks about this concept of momentum for the first time, which is kind of similar. It's really the quantity of material that's in motion. It's very similar to the word energy that we'll deal with later. And then he also introduces this concept of force, which is really interesting as well. So um, Newton, it's just, for me, it's quite interesting. You know, Force sounds a lot like Star Wars to me, right? Like, the Force did it. You know, it's like, what the heck are you talking about? The Force did it. But at the same time, he's really he's trying his best to keep this quasi-religious thinking out of it, to keep supernatural explanations out of it. And when someone would say to Newton, like, well, you know, what, like, we're going to see how he attributes this magnetic effect of the sun on the planets to this force he calls gravity. And people would say, Newton, what causes the force of gravity? He would say, that's not my problem. I don't know. And nobody, and in fact, not only do I not know what it is, that's not our job as natural philosophers, which is the word they had for scientists in that day. It's like, it's not the job of the scientists to figure out what causes it. Our job is to write really nice mathematical equations that describe how these parameters interact with each other. And he sets up this tradition because this guy is like basically a god to everybody who comes after him. I mean, the amount of, he sets up all of these force laws, right? He deals with inertia with this very, very, by the way, these are probably more familiar, let's see. These are probably more familiar ways you've heard them before. He sets up these laws. He has this huge magnum opus called Principia, where he lays out the foundations of physics and basically how we should go about understanding the world ever after. And people do it. This is essentially the same thing you probably learned if you took physics. Did anybody take physics in high school? A little bit? A couple of you? Yeah. Uh, these are the basic laws you learn. You know, F equals ma. Um, well, that's a story of inertial, the difficulty of moving something, right, and the force that must be applied to fight against inertia. Um, so he sets up this series of laws, and it's basically unassailable. And people embrace this project, but they also embrace Newton's idea that perhaps some things can't be explained, which is a really, really interesting moment, actually. Um, and I actually see this as a really good example of how really bad ideas can be mixed in with really good ones as well. So Newton sets up a tradition, and he really engraves this because he realizes, I'm going to skip the mathematics of this. Um, he really realizes that if you had the quantity of matter scale the speed and power of these orbits, that you could take away that uh, proportionality sign that I was talking about earlier, and you could replace it with an equal sign by essentially setting in the mass for each of the bodies that are operating in the solar system. Um, he's a little bit squidgy about what he means by mass. And that's kind of interesting too, because I think mass is still, we could probably have an entire course on the search for understanding what the word mass means. But Newton sort of means something like a quality that all bodies have, which more or less represents how much stuff is in a given unit volume, right? It's kind of related, it's loosely related to density, sort of like just the amount of stuff that's there. That's about as far as he goes. He's actually very comfortable with swapping out the word mass for body. So if you guys were in high school physics, sometimes they'll refer to like, there's a mass on a table and it's moving and the friction constant, you've heard this kind of thing maybe. Perhaps another nightmare too, because again, this word mass gets swapped out for body, but it's weird because some bodies are made out of lead and they have more mass, and some bodies are made out of styrofoam and they're the same size, but what's going on? Maybe they even have the same number of atoms, but one's heavier than the other, one has more mass than the other. Well, that's weird. Why is that? Why do some atoms have more mass than others? You know, there's this great periodic table thingy, right? I don't know if you guys can see that, but without raising this thing, there's a periodic table. I mean, these guys down here, this one's 257 times more massive than hydrogen. I don't even know what that is. LR? I have no idea. Some huge element. It's probably made in a laboratory or something. Why? Why is LR? Can somebody look up what LR is for me? Why is the LR 257 times more massive than hydrogen, and what the heck does that mean, right? That's a deep question that we can return to. Lawrencium?
A synthetic highly radioactive solid actinide metal. It was first synthesized in 1961.
There you go. Yeah, all these ones down here tend to be kind of synthetic. We make them and they only last for a few seconds or something. But so Newton kind of just he puts this together. He has this vague sense that the amount of material matters, something about the matter itself that matters too, but he doesn't really deal with that. So the cool thing is, and he deserves plenty of credit for this, and it's a really, really brilliant insight. And it's kind of shocking that Kepler didn't actually just stumble on this himself. But he realized that all he had to do to put an equal sign in Kepler's equation was to stuff in the product of the two masses of the bodies. Really, really simple adjustment, and it explains why some of the planets move faster than the others. Yeah.
Is it product or sum?
Sorry, some. Good catch. Yeah, that makes a lot more sense. It is the sum. The sum. And, you know, it's an interesting, first of all, it's a little bit circular of an argument. It's a cool idea, but they didn't have any way of going and deducing the mass of Jupiter, right? They could be like, well, Jupiter's bigger, and if Jupiter was bigger, then it would make sense that its orbit would be proportionally faster than it should be otherwise, right? So it's an argument that is in some sense a hypothesis, because if it's true, it's sufficient to prove out this relationship that Newton was hoping to scale and stick that equal sign in. Now, depending on where you're at with things, and we'll get to all of this later, we've sent lots of probes to Jupiter at this point. We've measured its gravitational tug. We have some sense of the mass of Jupiter, and it seems to be in accordance with the mass that's predicted from this, 17th century prediction, right? So it seems like Newton got it right, but it was far from a proof at the time. So that's kind of interesting. Okay, so Newton reworks this. He rewrites the relationship between this attractive magnetism that Kepler was talking about in terms of his forces, right? Because his entire Principia is written on the basis of this force system, where the efforts are in proportion to masses and accelerations, right? He rewrites it in that sense in terms of the effort that's being supplied, the gravity, he refers to it. The force of gravitation, right? What's pulling on it is now a force for the first time. And everything is quantified in terms of the forces. Now, this is, like I said, this is interesting. Quantitatively simplifies things. We actually have an equal sign in the equation. We can actually understand that the attraction is not just the sun, right? It's like, it kind of gives things back to the geocentrists a little bit. It's like, oh, the Earth is still important, don't worry. So the mass of the Earth matters too in determining the orbital dynamics, right? But we have to sit with this idea that there's still a mysterious force at the heart of what's happening here. Something about the sun and the Earth is causing them to pull on each other. What is going on with that? Now, like I said, Newton didn't really want to deal with it. He didn't seem to really think that that was much the job of the natural philosophers at the time. He thought that describing what's happening was perfectly fine. We have uh, we have some interesting ways of looking at this. So I think that will we do this semester? I don't think we'll get into general relativity much in this semester. I think it's more next semester. Needless to say, Newton's idea of gravitation, his description of gravitation, held out for hundreds of years, and in all honesty, NASA still uses it for the most part to send their rockets out into space. Um, there is a more accurate version, which comes from this formulation of general relativity in the 20th century. It's a little bit more accurate in some cases, but generally speaking, it's not that much better. And at the end of the day, it also is more of a description of what's happening. The real question about what's holding one object to the next really is an open topic. And so, when you're trying to visualize this, what this force law actually means, what is it saying? If you want to have a picture in your head of what's going on, a really good way to visualize it, I think, uh, is what's drawn over here at the left. And this is also, by the way, the same intensity plot for light. So light gets weaker with an inverse square law. So when I say inverse square law, I mean the further you go away, that r squared, uh, as you go further away, you decrease the intensity of gravity, or the intensity of light falls off by a factor of your distance squared, right? So it actually falls off really pretty quick. You don't have to get all that far away from Earth to feel almost no gravity. Light, similarly, I mean, you've probably tried this. You can have like a pretty bright, like a truck's headlamp that would like blow your eyes out. But you get down the road, a half a mile, and you can hardly see it, right? So both these things fall off pretty precipitously. I found this really interesting. So there's a visualization that people use often for light and for gravity. What's interesting is that, remember, I mentioned those Islamic scholars in the early Middle Ages. There's some writing by this Islamic scholar named Al-Tabiri, who actually describes this effect here. But the way he imagines it is that there's these invisible cords that are actually holding onto the earth from the sun. And through the implication of the geometry, the presence of the cords actually sort of falls off with in terms of how many area units that it would penetrate over the course of the distance from the objects. I think this is actually a pretty cool way of visualizing how we might think about gravity, only because what's quite interesting about atoms in general is that when you look at the surface, when you look at an atom, you guys remember studying like these orbital diagrams, maybe in high school chemistry? They have like these nice shells. Let me see if I can find a picture of one of these things. Or maybe I'll just draw one. So maybe you've seen like a hydrogen is just like a sphere, right? But then you move on maybe down to beryllium, or you move into, you get some, they'll say like it's added mass to the atom at some point. It's got more electrons perhaps. Whatever they're doing, they're making a bigger atom, right? And you'll see these other shapes starting to appear, like these little p orbitals start to appear, stuff like this, right? Well, the way that they actually determine these the shapes of these atoms, at least in this theoretical sense, and there's ways that they've kind of validated some of this in the laboratory. What they use to actually draw the shapes is something called the wave function for the electron. So they assume that the outer surface of the atom is the electron. You guys maybe have heard this before, right? There's a nucleus, the electron is doing something orbiting the center of the atom. The outer surface, for at least for the purposes of the chemists, is an electron of some sort. It's got an electron shell, they'll often say. What's quite interesting about the electron shell is that these structures are determined from the wave function for the electron, which is beyond the scope of what we're doing right now, but it's important because what happens is that to get this shape, you actually ask a sort of question of the wave function, which is something like, if I start at the nucleus, let me draw this over here. So let's say this is a graph This is distance from the nucleus. So this is the nucleus right here. We'll just put an N there at 0. And I ask, where's the surface of my atom at? Where's the electron? Where am I going to find the electron? Well, you don't really find it at the nucleus, but at some distance in the nucleus, you find it. And then you're not going to find it, and then you're not going to find it, and it kind of falls off like this. And we say that this is the surface of the atom, is kind of where we're most likely to find the electron. But what's totally bananas and really, really interesting is that this actually never hits 0 down here. You're actually always capable of finding that surface of the atom at any distance from the nucleus. That's really, really interesting. It really makes it seem like the atoms that we see in the chemistry books with these nice, beautiful shells and stuff, it's not quite right. It's almost like there's some sort of really thinned portion of these atoms that actually reaches out quite far to their, at least to their neighbors, perhaps really, really far. I kind of think of them as being sort of furry or hairy in some sense. You know, the idea of a cloud was quite popular for a while, but clouds are weird because clouds don't have any way of actually pulling on one another. But you can imagine that if there's some thinned portion of the surface of the atom, you might actually have something that's a little bit closer to what the Persians were on about with these bodies being tethered to one another in some actual physical sense. So something, more food for thought, something to think about. You know, from in Newton's day and well after Newton's day, all the way up until the turn of the 20th century, most people assumed that there was some sort of invisible stuff in between us and the sun. They didn't know what it was. They called it the luminiferous ether because luminiferous because it supplied, it was the medium by which light traveled. It was where the light was traveling. Light, yeah, it's glowing, right? It was also the medium by which electric force was transmitted at a distance, magnetism, gravity, basically all the invisible stuff that makes no sense otherwise, right? So they had this kind of stand-in idea. Nobody, even Newton, he leaned into these ether ideas too, but he didn't understand the mechanics of it. It gets really weird when we start looking at what light is, and we'll have plenty of time to do that, and I'll show you why people kind of gave up on this ether idea. They couldn't solve the riddle of how it was that this medium was able to do all of these different things. And so we live in a really interesting point in the history of science right now, because people basically gave up on that problem. They didn't solve the problem. They didn't solve the problem of what it is that holds us to the earth right now. Why are you sticking to the ground? No one really solved that problem. They came up with really, really, really accurate descriptions of how it is that you will appear to stick to the ground. In fact, they can, you know, the accuracy and the predictive power of that is extraordinary, to the tune of us being able to send spacecraft out into the outer reaches of the galaxy quite predictably. But in terms of the actual mechanics of that, the same goes for light, the same goes for electricity and magnetism. The descriptions, almost in a very, you know, dangerously close to Ptolemaic sense, are really accurate. The equations we have, Newton's equation for gravity, it works really, really well. But what the heck is this force thing? What is going on? What is the actual hidden story between what it is that grips you to the ground right now? I mean, that should be really exciting to you, right? Because we're actually living in this really funny moment where it seems like we're so sophisticated and technologically on top of everything. And we are. But there is a story that comes later where people look back on this moment and they say, oh, these people didn't understand how this works. They were really good at describing the mechanics of it, and they built spaceships and stuff. They had no idea what held them to the ground, actually. That's pretty cool, I think. I think that's really exciting. The same goes for the other big four mysteries of physics: electricity, magnetism, light, gravity. So, yeah.
Do you have any contemporary theories of gravity that you sort of lean toward?
Yeah, absolutely. I tried to sort of very subtly suggest one to you just now. I think that the atoms have an extended architecture, essentially. So I think that it's not that's not a radical idea. I'm just interpreting the wave function. I mean, I'm kind of making this realization that how do we know what an atom is shaped like? We know the shape of the atom from the electron wave function. The electron wave function does not say that there's an actual end to the shell of the atom. It says that it's actually gets quite rarefied, almost thinned out, low density over here. I believe that it probably has some sort of structure. That's why I kind of think about it as furry personally myself. It's able to bear tension in some sense. Um, and I think we can learn a lot about the structure of that medium. But I think it has to be a structured medium. And this will make more sense when we start talking about light. I think the reason that people gave up on a luminiferous ether was that they imagined it to be this kind of homogeneous fluid. And a homogeneous fluid doesn't conform to the requirements necessary to perform really patterned behaviors like light and magnetism and electricity. Those are really patterned phenomena. And in order to pull off that task, you have to have a very structured medium to do it. You can't just have this kind of like nebulous fluid that just does stuff. You have to actually start supplying structure to it. But I think that the more that we start to think about things like electricity and magnetism as the actions of the surface of this atom, as motions of the surface of the atom, and its extended architecture relaying those motions to its neighbors, and there being this chain of relay that plays out and explains all the phenomena, I think we can actually come to really rational explanations that are completely in line with all of the mathematics that we already understand. So, yeah, so I have some ideas about this stuff, but there, you won't find too many of them out there. Is the weird thing, right? There's almost everybody I talk to, um, almost everybody I talk to is content with the equations themselves. It's kind of like, who cares? That's actually my favorite thing to get from people. It's like, who cares? It's like, well, because it might matter, like, who knows what we're missing out on? Like, yeah, we have really cool technologies right now. We can, you know, throw satellites at the moon or whatever. Well, like, if we actually comprehended like a mechanical basis for how these phenomena, like, if we actually understood what held us to the ground, maybe we could work around that. I don't know, maybe that would be cool. I have no idea, but I do know that coming into more crisp pictures of what causes phenomena can spark incredible revolutions in our own quality of life and our technological ability. Um, you know, Fusion is a great low-hanging fruit I could pick on. I think that if we misunderstand materially how it is that atoms combine and release energy, we might never ever be able to build the kind of reactors that could spare us from having to burn trees in the stupid ways that we often, you know, we burn stuff in these tanks to move our cars around and stuff. It might be unnecessary, right? If we understood how the atoms actually did their magic rather than just the equations for how they do their magic. The equations are cool, but there is a story, right? The equations are not the hand of God. They just describe the patterns that you're capable of witnessing. Yeah,
I'm just trying to like conceptualize what you're saying with
yeah.
reaching out and not being and furry. Would you say that it's more like I'm just remembering that image on the first day of class of like the universe and the galaxy
Mm.
out, like it almost looks like a Pullman quilt.
Yeah, yeah.
Right.
That would make a lot of sense to me. Yeah, if the small scale looked a lot like that. Yeah, I think that the problem is that there's no real rational visualizations for what's happening. You can in textbooks you'll see that there's little part like the atom's got like, it's got like a little like plus point in the center, and then there's like a minus thingy, but like nobody who actually works with these things thinks about it that way. They think about it in terms of fields of influence, right? They think about it like, well, there's something over here that's doing something opposite of this thing over here. And like, there's a very nuanced build out of what's happening, but literally nobody thinks about it in terms of these little dot things that are just doing magic to each other. That's just like a convenient lie that they put into textbooks because it's easier to do the accounting in that sense. But nobody really thinks that's happening. The problem is that nobody really thinks about it at all. Like it's not important because by parameterizing it mathematically, you can do incredible works of magic, such as Zoom meetings and cell phones and rocket ships, right? So it's an interesting orphaned piece of the puzzle. And so, yeah, I think that the only way that you can hold one thing onto the next is through tension, right? So, like my own PhD that I did was largely about how water does incredible acts of tension. Actually, water can supply, the mechanical strength to an object that approximates, something as strong as this table just by tensioning the water molecules inside of it. And you're like, what the heck does that mean to tension water? And it's like, well, the actual molecules are in some sense entangled. They're literally ground, let's say, enmeshed with one another. Right? There's some sort of frictional element by which the surfaces of those atoms are actually wrapped up in each other and pulling on one another. And so I think that, and look, I'm not telling you I'm right about this. I'm just, you guys would love to hear some pushback, but from where I'm sitting, there's no way to conceive of tension with particles doing things. Like you can't have bowling balls supplying tension. It doesn't work. You have to have some sort of fibers that are entwined, which are pulling on one another. That's literally the only thing I don't think anybody can conceive of anything to supply tension other than entwined fibers of some sort. And so, yeah, it wouldn't surprise me one bit if it turns out that the organization of the atomic world is very much some sort of web-like structure, much like we see at the large cosmic scale. Yeah.
I have two thoughts. One, um, I feel like a lot of these current questions and mysteries are part are sort of something that might later on in science be explained by a new theory that reconciles like quantum mechanics and general relativity because we don't know there's a whole thing where those two don't really work together.
Oh man, I know.
Um, and my other thought was maybe that missing thing that connects everything. Like I feel like our idea of gravity is a similar idea to what luminiferous aether was. Like we have this thing that can explain it, that can describe what we,
Right, right. It's a placeholder for sure.
but maybe there is just a thing in aether, just a thing that connects things.
Oh, I think there has to be. The question is like, the question it never gets past. First of all of the super brilliant eggheads that I talk to, right? I'm in this awesome position because I can just call these people up. I have this podcast. It's not huge, but we have like tens of thousands of listeners, and so people talk to us. So I call up these like super brilliant eggheads at Oxford and Cambridge and Harvard and MIT, and they sort of they sort of recognize that there must be some sort of medium that conveys these forces. There must be something happening there. But it's not an easy question to solve. It's not a simple fluid thing. It's not anybody who's just like, well, it's the ether and stuff. It's like that's no better than it's the force of gravity. Because a fluid can't do this dance of light that we're going to talk about later, which is really conveying a change in polarity of the atom at a distance. No, I know. I'm just saying that the word ether is generally associated with some sort of fluid that just does whatever you want it to do. I think that the real like difficult part, what I'm trying to say is like you have to whatever comes to be understood is going to structurally accomplish what the ether could not structurally accomplish. It's going to be there's absolutely I just don't think that I don't think you could rationalize two things holding on to each other. Look, it's your choice. It's either magic or there's some sort of structured medium that's doing it. And so, you know, as a science professor, I'm inclined towards the structured medium is doing it. Solving the nuances of that is an incredibly laborious project, and it's one in which I'm very much involved and interested. Yeah.
I like to really to share this because it's like kind of ridiculous, but then since you said magic, I guess I will. I was thinking like, what if it's just nothing? Like it really is just the force of gravity. There's like no way to explain it, no matter what we ever like could do with it, or like you get to the point where, however you could observe it, I guess, like you look and then there's just like nothing.
Yeah. Well, that's the kind of the alternative, I guess, is where I'm sitting. And it's like, maybe But why would anything make any sense if that was the case? Like, why would there be mechanical cause for anything if that was the case? Why wouldn't everything just be completely bonkers magic that just made no sense? Like, stuff's just doing whatever, whenever, and it's completely inexplicable, and the world is just. It doesn't seem like that's how the room around us is organized, and I don't see any reason to suspect that any part of reality is like that. I mean, perhaps there's a highly abstract level of existence. I'm certain there is, which you would have a hard time explaining with atoms. Love for your significant others, your family members, the relationships, your passions, the motivations, what gets you up in the morning. Like, I don't think you're going to be able to explain that stuff with atoms. I think it would be a fool's errand to try. But when we're talking about the stuff that atoms do, like, it's probably the atoms doing stuff, right? It just seems like that's how everything else in the room works. Yeah, Andrew.
So we're sort of, this is one of my favorite topics, but
Heck yeah, let's do it.
just in case this conversation is really interesting to anyone else, we've sort of been dancing around one of my favorite pet theories, which is the Eric Berlin entropic gravity theory. If anybody's interested in that, I can send you a link to a video about it or whatever. But it's
Yeah, what's the difference from like the Newtonian picture? Or is it just a descriptive
and the way that it was described to me that kind of clicked with me a little bit is as whatever we call mass, whether it's a field or some kind of atomic structure or whatever, as that accumulates by whatever means, the entropy around the that mass accumulation, I believe it decreases so that the spin of the quarks in the vicinity of it begin to align in a particular direction. So it might pull, if you think of the, I'd have to draw it almost get this out of my head, but you're basically all of the, if you think about like when you have a magnetic material, all of the, we have like a linear direction of the, I can't think of the terms right now, but
Yeah. Yeah.
the poles line up, right? And that's it. A similar thing is happening as the mass accumulates in a particular location. Is that the entropy of the spin of these quarks all start to point in the same direction. Has anyone seen ferrofluids?
Yeah. For sure.
People have in they have like the spikes. Is it like kind of like that where they sort of point toward thin?
I mean, look, the difficulty is you have to start asking yourself like huge questions, like what's in a quark, or we could even like like what do we mean by electron? What are we talking about? But I think that you're right that there is. I think it is certainly some sort of network effect of the atoms as they interact with each other in their surroundings, and however you want to parameterize that. I mean, we haven't even talked. We can't talk about entropic theories of gravity because we haven't talked about entropy. We will, I think, eventually, but there's like a lot of subcomponents nested in that. But at the end of the day, like the atoms have to have some sort of actual architecture, and they have to be doing something to each other. And now, however you want, you want to bust that up and try to make sense of it. I think all of these pieces really do each have something unique to contribute. I've heard a lot of really interesting descriptions in terms of like that sound very similar to this. But at the end of the day, most people are really, really, really resistant to the actual assignment of architecture to the structural elements involved. And I think that that's what it takes for a human being to really comprehend something fully, is a real physical picture of what's going on. A quark, again, a quark isn't, I'm going to just cut to the chase, like a quark isn't a material object is the thing. It's a pattern of motion, some sort of material in motion. It has a particular motion assigned to it. It's more or less a predictable pattern of motion that we can detect under certain circumstances, but what the heck is moving, right? And I would say it's probably some part of the atom that's moving. And I would say some structure is doing something. And so I think building out that picture more and more is really what this project is going to amount to in the coming, decades, centuries, whenever people really grab it by the horns. So, yeah, this is and I'm glad you guys are interested in this because it's going to keep coming up. Many mysteries come down to fundamentally swapping out equations for reality, and we've seen the cautionary tale of what can happen when you do that. So we have to be really careful about it going forward. What else? Thoughts, questions? Anybody on this side of the room? You guys have been kind of quiet. Freak you out with all of this mathematics and gravity stuff? Sorry. It's pretty weird that you're sticking to the floor right now, though, right? You gotta admit, it's really it's uncomfortable if you sit with it quietly for too long. One sec, Corey. Yeah.
One stray thought that just, I hope if we do discover a medium through which everything is being transmitted, that we call it the ether.
It's a cool name, right? Yeah, absolutely. That's yeah.
I think we might, the discovery of what basically connects everything. I feel like that might come after we figure out how the human brain works fundamentally.
It does seem kind of similar in some ways, yeah.
I feel like there's a certain barrier to human conception of such abstract ideas.
Yeah. Well, I'm struck by how much that cosmic web of galaxies looks like a neuronal architecture. I've always thought that's just so weird. It just looks like a bunch of neurons. It's so bizarre. So yeah, I don't know. Jury's still out. There's a huge, I'm wanting you guys to be more aware of the mysteries than of any particular solution that I could advocate for you right now. But I do believe these are solvable questions, to be honest with you. My wife and I have been working on a book for almost 10 years. We're trying to supply our own particular understanding of this, but that's not as important as recognizing that there is a mystery that's really there to be solved. And what's that?
That's what makes science interesting.
Yeah, that's what's cool. That's what you guys should be excited about, honestly. It's like, yeah, great. We understand the force of gravity is proportional to the masses. That's cool too, but like, why? Why is it like that? That's a huge amount of work to be done, and people will be arguing about it. Even if somebody steps up and provides a solution that's totally awesome, right? And who wouldn't love to have that insight and be able to do that? That person's probably no one's gonna care. Like people are gonna be like, whatever, we don't need this. That's kind of how it goes. Copernicus didn't win a Nobel Prize, my friends. Like, nobody patted him on the head and was like, good job, boy. Like, it's not how it works often, right? So, it'll probably be centuries. The very smart solutions may appear, and they may be, who knows how long they'll lay there and be passed over or derided or whatever before people before maybe even some experiment comes along that just validates it too, and it becomes undeniable. But these paradigm shifts of this scale could be really prolonged and take a long time. So
Makes me think that as much as we revere Einstein, that his theories might go the way of Ptolemy
yeah,
as soon as we have a better understanding.
yeah, he understood that too. You've been reading a lot of Einstein's letters for this book we're working on, and he knew that he hadn't nailed this problem. I mean, he had a really good description of what was happening for sure. Really accurate. But he
Could also have that is like we could end up thinking of it similar to the guy who measured the circumference of the Earth, right?
and then it got forgotten about.
Basically, almost got it right with such basic tools.
Yeah. There's probably a lot of. I personally have found tons of clues in the past. People whose writings nobody ever would come across, who were really troubled by a lot of these issues, made good progress on it that you'll never hear about. So yeah, you do got to mind the past for sure. That I think both things happen. But I should let you guys go. We will pick up with this mystery, and we'll keep pressing on. We'll move on from here into. I guess we're going to get really into orbital dynamics and start talking about our own orbit, stuff like that. So have a wonderful weekend, guys, and stay curious. Yeah.